Hello, my name is Lawrence Killer, and this is another application of Q-Learning on the Open Race Car Simulator, also named TORCS. TORCS is, as it says, a racing car simulator, which can be optimized for reinforcement learning agents. It has a lot of building cars and tracks, and also features or featured in the past yearly championships. Our setting today is only one car in a race, which will be our agent. A relatively simple track for learning. You can see it in the top right of the video. The gear shift will be automatic, so we won't care, or our agent will not care about when to shift between the gears. The episode ends when the car leaves the track or when it finishes 10 laps, and we will train steering and acceleration agents separately, one after one. So for the steering agent, we first define 3 possible actions, which is going straight, going left, and going right. And we will use a constant value for gas of about 25% of what is possible. We will only use 2 sensors, which are both mapped to 21 substates. That means we have a total number of 441 states, and times 3 is 1323 entries in our Q table. The sensors that we use is number 1, the horizontal position on the track. The sensor is 0 when the car is in the middle of the track, 1 or -1 when it's on the edge, and more than 1 or less than -1 when it's out of the track. And we will use the car angle. This values range between pi and -pi, but we will only care about the front half because I don't want to care about scenarios when the car faces the back, like to the back of the track. And as a reward, we use 10 times 1 minus the absolute of track position. That means the reward is 10 in the middle of the track, smaller if it's not in the middle, and negative when it's out of the track. Also, when the car leaves the track too much, so past these 1.3 boundaries, we will give a reward of -1000 and restart the episode. The Q-Learning parameters this time, as I said, the reward is like this. The discount factor is 0.8 gamma, the learning rate is 0.2, and we will start with a random probability with an epsilon value of 0.75, and we will decrease it by 0.003 for every episode and cap it at 0.001. That means when we learn our agent when we let it learn for 500 episodes, it has both time to explore the environment and later on exploit. And after these 500, we will set epsilon to 0 and optimize it without any randomness for 50 more episodes to have a finished agent without randomness. When we do this, here on the right, that's how it looks like. We have a car that can finish the race without any problems. It goes about 75 kilometers per hour. And when we look at the left at the graph, so these small points are the time steps, how long the race lasted. We can see first it had struggled to learn, but then when epsilon got lower, it suddenly had successful episodes and started to learn. And when we turn off the epsilon altogether, you can see that it optimizes on one value, which is a bit lower than the maximum, but that just means that the race finished earlier, which actually means that we had a more optimal behavior than in these scenarios, for example. And now to the acceleration agents, I defined 4 possible actions: full gas, only little, no gas at all, and even braking. And we're using the trained steering agent from before and 2 sensors. Both of those sensors are mapped to 10 substates, so that means 100 states in total and a Q table size of 400 entries. So the sensors we use this time is number 1, the central range sensor, which just tells us how far away is the nearest obstacle, and the car speed. How far is the car currently going? And as a reward, we use again the track position because we want to reward if the car stays in the middle of the track, and this time also the speed, so we want to reward when a car gets faster. This time I use a value of negative 10,000 when a car leaves the track, because we really do not want this to happen anymore. So the Q learning parameters, as I said, the reward as is, discount factor 0.8 again, learning rate 0.2, random probability starts at 0.75 and is decreased by 0.035 for every episode. We cap it again, and in the end let it train for 250 episodes like this, and afterwards with epsilon 0 for 50 more episodes to optimize. And if we do that, those are the results. Here the car, it looks very similar to before, but this time we can see that the car actually goes faster. It goes about 80 miles per hour, and it also is in a very much higher gear shift, so it actually presses the gas button way more. But we can see that in the curves it will get slower, and that's the behavior I like most, because it means that we are also performing better on other tracks with more strong curves. And on the graph here we can see at the beginning of the training it took some time to finish the race. Here it improved upon this, and in the end it even crashed sometimes, so those are episodes when we didn't finish the race, but once we turned off the epsilon again it could optimize on a value where it doesn't crash anymore and finishes with about 80 kilometers per hour. Yeah. So if we apply this, so this is the track we trained on, and if we apply this to other tracks, we can see that we successfully can finish a lot of different tracks. 3 more where we crash once or twice into a wall, and then there are a few which are just too strong curves, or for example, in a lot of them you have walls too far away, so our range sensor doesn't find them. So this is by far not the most optimal agent that one could do, but I really like it, and I have to say that I don't have any more time to continue playing around with this. So for now I'd say thanks for watching, and yeah, that's the last video. Bye bye.